More and more researchers have acknowledged the superior explanatory power of a new computational model of cognition that refutes a linear track in perception and action, embodied prediction. This model proposes that since the body is adaptively built for maintaining homeostasis, it subliminally uses a predictive process in both A, representing its inner and outer environment, and B, acting upon it according to the bodily system's goals. First, the body uses multimodal summaries of neuronal pattern activations called simulations to represent sensory input. This means that while a grouping of sensory input at hand may be received through one sensory modality, the brain will partially reenact a summary of the neuronal activation patterns from all modalities from previous encounters with similar groupings. For example, at the sight of an apple, your brain enacts not just patterns of neuronal activation for color, shape, depth, etc., but it also simulates those which had occurred at an apple's crunchish sound, the sweet taste, the smell of an apple pie from last year, the proprioception of clutching one, etc. Second, the body predicts what simulations will be activated when both representing the world and acting upon it. When representing the world. A. The body uses past experiences to anticipate incoming sensory input with a supply of ready-to-go latent simulations that are sent to sensory cortices so that they are accessible to be compared with present incoming sensory input from any sensory modality. When light waves enter through the vision modality, many predictions are available to the visual cortex, one of which is a multimodal summary of activation patterns for apple. B. The signals of those light waves, however, won't be used completely by the brain. The visual cortex only uses signals from actual incoming sensory input in two ways. The first way is to select which simulation most matches it. The signals from sensory input that were correctly predicted are discarded due to redundancy. The second way signals from sensory input are used before they are discarded is to correct and update a simulation when the best suited prediction does not match present sensory input appropriately. In that case, the signals from sensory input replace the simulation's visual cortex activation patterns, which were wrong. This gap in prediction corrected by signals from exogenous input is called prediction error. To minimize prediction error, simulations are corrected to more appropriately predict future sensory input. This predictive function of modeling the world by inferring the causes of sensory input is called causal inference. As I mentioned before, predictive processing has also been proposed as a basis of action. When the body needs its inner or outer environment to change in order to achieve a better homeostatic physiological state, the brain will send predictions to the body of how it wants its physiological states to be. For example, the brain will send signals to the muscles in your right arm that predict the proprioception of those muscles moving. Since your right arm isn't actually moving, there is a prediction error. The muscle cells will attempt to minimize the prediction by assuming the desired physiological state. The muscles will contract, resulting in your movement to pick up the apple. This is called active inference. If the brain can predict well, that means that it can anticipate homeostatic boosters or hazards with counterfactual physiological bodily changes in position before sensory input even confirms the need for them.